Welcome to Hot Chips 26. Session 8, Big Iron Servers.
So I'm Alan Smith. I'm the session chair for the last session of the conference, the Big Iron Server so-called session. This is the one, the joke about the 800-pound gorilla and where does he sleep. So we've got three 800-pound gorillas, and they get to take over the stage in serial form. Our first speaker today is going to be Alex Mericas, who is at IBM Austin. He's a senior technical staff member at IBM in the system performance area. He began his IBM career as a software performance analyst in IBM Software Group. He moved to hardware performance as part of the performance team for Power 4. He designed the performance monitoring hardware on Power 4, Power 5, Power 6, Power 7, and Power PC 970. And I'll add a parenthetical remark that I'm glad to see that there's at least a design that left the performance monitoring in. In days when I used to consult heavily, somehow when the schedule got behind, you say, well, what can we leave out to make deadlines? Oh, the performance stuff, we don't need that. He's currently the performance architect for Power 8 and Open Power. He's an IBM master inventor with 35 issued patents covering microprocessor design and hardware performance monitors. Oh, a couple of announcements first. By the way, you guys all should have review forms in your packet, so before you leave, please drop your conference evaluation in the box and tell us what you liked and didn't like. And at the end of the session, don't run off. There'll be closing speakers for 5 or 10 minutes. So Alex's title is Performance Characteristics of the Power 8 Processor. Alex?
Thank you. So at least some people recovered from the ice cream. When I saw the line out there for the ice cream, I said, I don't know if this is a good thing or a bad thing that I have to go after ice cream, but we'll see. Today, I'd like to talk to you about Power 8 and specifically the performance characteristics of the Power 8 processor. The Power 8 processor was designed for big data and it was optimized for analytic performance. Now, what do I mean by that? There are three attributes that we've determined are necessary for big data and analytics. The first attribute is you need strong processors, lots of them. Also, it helps to have a lot of threads of execution. The second attribute is you need a lot of fast memory, big data spaces, and the faster the better. And then the third is, that goes along with that, is it's not particularly helpful to have a lot of data if you can't get a lot of that data into the processor. So you have to have a lot of data bandwidth, and both memory bandwidth and I/O bandwidth. There's a fourth component that's not on here, and that fourth component is we found that a lot of the software, most of the software that's currently being used for big data and analytics is written in Java. Remember, there was a question before for the text analytics session of why Java? Well, the answer is quite simple, because that's what it's written in. So a lot of these big data and analytics routines are written in Java, and if you want to be successful in that, you have to do well in Java. And I'm not going to go into a lot about Java technology because this really is a hardware conference, a chip conference, but as you'll see as we go on, we do quite well in Java too. So first I'm going to take a walk down memory lane. If you remember last year, if you attended last year's conference, my colleague Jeff Stukley came and disclosed the Power 8 processor. So I'm going to go over kind of briefly the contents of last year's pitch. I don't want to spend too much time on it, but it's more of kind of like a memory refresher. And remember the attributes that I talked about. So the Power 8 processor is an 12-core SMT8 processor. It's got up to 230 gigabytes of memory bandwidth, and it's got big L2 and L3 caches. It also has a feature, and I wish I'd put a chart in this later, we talked about CAPI, the CAPI interface. If I have time in my session, time in the question and answers, if you had some questions that you weren't able to get covered, we could do it then, or after the session, I'd be more than happy to talk to you about CAPI technology. So we have 12 of these cores on the chip. And these cores are significantly beefier than the Power 7, the predecessor Power 7 processor. In order to make room for SMT8, in order to be able to double the number of threads that we support, we literally had to double the core. So what we did is we doubled the D cache. We doubled it to 64K. We doubled the data paths within the core. And in many cases, we doubled the execution units. We've always been a wide dispatch, wide execution processor. We now can dispatch up to 8 instructions at a time. We can execute up to, we can issue up to 10 instructions at a time. And we have 16 execution pipes that can all be running simultaneously. Within that 16, we added 2 additional load units. We always had 2 load store units. We've added 2 additional units that do load only. Now, both these load units and the load store units can also do simple ops too. So we've also significantly improved our simple ops, things like simple integer operations. And we've just generally increased the queue sizes, and as I said, the data paths within the core. The other thing, just as a reminder from last year, is we have a very beefy memory subsystem. We have 8 channels of memory, and this is a memory technology agnostic channel that we use. We call it a DMI channel that talks to a buffer chip. And then behind that buffer chip, we could have either DDR3 or DDR4. The interface is agnostic to the processor, so it doesn't matter what technology you're using. And at initial product availability, we support 1 terabyte per processor socket of memory capacity, and this interface can support up to 230 gigabytes of memory bandwidth. Now, to go along with the large memory space, we have to be fast. I already talked about the memory buffer chip. It has an onboard L4 cache. Now, the L4 cache does 2 things. One of the things, since it's a cache, obviously it reduces the latency to local memory, but it also absorbs some of the traffic to the local DIMMs, and so it reduces the energy use of those DIMMs and makes the DIMMs more memory efficient. So in addition to that off-chip cache, we also have significant on-chip cache. You can see we have our L2 and our L3. We have this very sophisticated chip interconnect system. We have each one of these sections has its own on-ramp to the chip interconnect. And each one of those, there's 16 if you count them, there's 16 interconnects, and they can each go 150 gigabytes per second per direction, per segment. A lot of bandwidth. As you can see, as a reminder from last year also, we have a tremendous amount of bandwidth between the caches and the processors. And those numbers, those are not data widths, that's gigabytes per second that we're transferring between the cache levels. So that's my walk down memory lane. Now I'd like to talk about the processor that we announced in April and started shipping in June. What we did, we took the processor that Jeff Stukley discussed last year. This is our scale-out processor. Our scale-up processor. It's actually optimized for large systems, large SMPs. It has up to 32 lanes of PCIe Gen 3. Of that, 16 lanes can be used for a CAPI device, and that's per socket. So you can aggregate that over the system for much more. And it's got the very large memory space that we talked about in bandwidth. But the first systems that we introduced were not these scale-up enterprise systems. They were the scale-out volume systems. And most of these systems are based around 1 or 2 sockets. And the first problem that we had is that if you ship a one-socket system that's based on this chip and you want to use our nice CAPI technology, well, two problems. One, you can only put one CAPI board in that one socket because only half of the lanes support CAPI. And two, you've just wiped out most of your I/O, including your high-speed I/O, your 6x16 I/O. So instead of using this in our scale-out processors, we took what we sometimes refer to as an X-Acto knife approach, and we cut the chip not quite in half, but roughly 60% down, and we took two chips and put them next to each other. And so what this allowed us to do was to optimize for the one-socket and two-socket space. We could still put 12 cores, 12 CPUs per socket on the system, but instead of being limited to 32 lanes of PCIe, we now have 48 lanes of PCIe, and we can put 2 CAPI cards per socket. Everything else is the same. The core, the L2, the L3, the L4, memory buffer, everything else. And what is pertinent to this discussion today is the performance characteristics of this version of the Power 8 processor are identical to the other version. Obviously, there are going to be differences in product offering as far as frequencies and stuff like that, but the base characteristics are all the same. Now, very briefly, I want to talk about these are the servers that we put it into. I'm not going to spend a lot of time on them. We have one-socket and two-socket versions of the systems, and we have 2U and 4U high versions of the system. We've also introduced versions of the system. The standard operating procedure for our system is it can run any of our operating systems, AIX, IBM I, or any of the flavors of Linux that you might be interested in. We have another version that is a Linux-only version, which is a reduced cost, but electronically it's the same as the other versions. And as you can see, I'm not going to go through this item by item, but we put a lot of electronics and a lot of hardware into that small space. And as you will see, we also put a lot of performance into it. So let's start talking a little bit about the performance characteristics of Power 8, now that I've given you a review of what Power 8 actually is. As Alan mentioned, I grew up in hardware performance. Essentially, my main job was designing instrumentation. So I kind of view the first thing that you want to be able to do is measure your system and be able to understand where the performance is, and maybe more importantly, where it's not, so you can improve it. So one of the things that we did on Power 8, which is a big focus, is we have this feature that we introduced back in the PowerPC 970, which is called the CPI stack. And what it does is it determines where the cycles spent processing each instruction go to. And the way it does that is it kind of looks back from completion. It says, what is holding up my completion? And once it figures out what held up completion, it assigns that to the entire dispatch group and said, okay, the last thing that cleared in that dispatch group is what held up completion, and therefore I'm going to charge off the entire group to that cause. As an example of maybe if the last thing in the group was a cache miss, condition that clear was a cache miss, it'd say, hey, you know, however many cycles this group was not completing was due to cache miss. And that's actually a pretty good method of doing things. It was very successful. We use it with a lot of success in Power 5, Power 6, and even in Power 7. But we had a couple of problems. One, there were a lot of cases where we didn't quite break down the reasons why we were stalling. So in Power 8, we added a bunch more of these reasons in. You can see all the things that are listed in blue. That's new with Power 8. About half of the things that are in the table are blue. So we added a lot of different breakdowns in our CPI stack. The other thing that we did, which was always kind of troubling, was, as I said, we attributed the last thing that completed in the group, last condition that cleared, as the reason why the whole group couldn't complete. And I always was bothered by this scenario that within a dispatch group, we'd have a long latency load feeding a single cycle add. And because the long latency load would clear first before that single cycle add could start its execution and then finally finish and complete, the last thing that cleared in that completion group was the single cycle add. And so we would charge off that whole delay to the single cycle add. And it just, one, it didn't seem fair, and two, it just flat out wasn't accurate. So the other thing we did in Power 8 is that we were able to break up these dependency chains. And so now we can get better visibility into some of the complex reasons that are causing completion stalls. Another thing we did, which we use with our instruction profiling, you know, I'm sure if you're familiar with doing software performance work, you know that one of the common things you do is run something like O-profile, where you profile the code to find out where all the time is. You can also profile on events like cache misses and stuff like that. And we've used that to great success. The method that we use is that we randomly pick one instruction at a time, we follow its execution, and if it occurs some of these events like a cache miss or a branch mispredict, we have a performance monitor event that's annotated with the fact that it's due to a sampled instruction, and we collect things like its instruction address and the data address if it's a load or a store. So if you sample on these if you profile on these sampled events, you can very accurately determine where they're occurring in the code. Well, that's fine for a single event at a time, or maybe two or three, depending on the limits of your counters. But what we did in Power 8 is now we have this event register for every event that happened to the sampled instruction we collect, including where load was satisfied in the memory hierarchy, branch mispredict, how many cycles it was stalled, why it was stalled, etc. So you can just profile on just the execution of a sampled instruction and then get all this. There are a few other things that we did to improve the ability to do monitoring on the software, including the ability to do dynamic code optimization. We heard from NVIDIA yesterday about their hardware that does dynamic code optimization. We have assists in the performance monitor unit that allow software to be written to do similar types of code optimization. One of the first things we do is we have sampled filtering. Remember the example I said you might have 2 or 3 different conditions you might want to look at. The standard way is that maybe you collect a lot of samples and then go through them and to see if you had multiple combinations. And you might have to go through a lot of these samples to get the 1 or 2 instructions you want. Well, now we let the hardware take care of it. The second thing we do is we have what we call a hotness table, where you define what hot means, whether it's a lot of cache misses or a lot of branch mispredicts, or maybe even just a lot of execution. And we have a hotness table that keeps track of the address, instruction address, and how hot it is. And when it goes over a certain threshold, it generates an interrupt. And so this code optimizer that you would write or somebody might want to write can then realize that, oh, I've got some hot address and I ought to do something about it. We've added a branch history rolling buffer so that it's basically like a callback thing, so we can tell how we got to a particular place, say an interrupt. And then the fourth thing that we did to help general monitoring and also code optimization is we added what we call event-based branches, or I like to call them user mode interrupts. One of the problems of using performance monitoring is that you usually have to call the operating system to configure it. The operating system takes the interrupt and has to reflect that back to the user mode code to do anything about it. Well, we now have the ability to set up these event-based branches which look to a user mode program like a signal. You set up like a signal handler. And so something like a Java virtual machine could catch its own performance monitor interrupts without having to go through the operating system and without incurring any of the overhead of the operating system. And all of these techniques that could be used for dynamic code optimization, I use the example of the Java virtual machine because our Java does use this and uses it to monitor itself and improve its optimization and JIT efficiency. So let's talk about some other things that we did with threading. Power 7 was a SMT4 machine. And The way we implemented it is we split the core in half, and we had two thread sets, thread set 0 and 1, and the threads were laid out like this. The even threads were on one side and the odd threads were the other. And that's great if you're running an SMT4 mode and you've got 4 threads active. But if all of a sudden your workload changed and you only had 2 threads active, and you were unlucky enough to have the 2 threads that were active being thread 0 and thread 2, then both of the threads were on one side of the core, and you had this other side of the core that wasn't being used, and the resources weren't available to either of these threads. So the operating system would then have to take some action. That first it would move the execution to the appropriate threads. Then it would do what we call a nap on these idle threads. And then it would make a call to the hardware to say, I've only got 2 threads now, so why don't you downshift into SMT2 mode? And the processor would have to quiesce and take a while to restructure everything and then move into SMT2 mode. And if it wanted to do the reverse, the operating system would have to realize, I've got sufficient load that I can now activate those other threads. Maybe I better switch into SMT4 mode, and it would have to reverse the process. On Power 8, we still separate the core into 2 thread sets. We have a thread set 0 and thread 1, and half the threads can run on one half, and the other half could run on the other half. But the thing that we did is, unlike Power 7 that had a static mapping between the thread number and the thread set, it's now dynamic. So if we start out where we're running 8 threads in SMT8 mode, and suddenly 6 of those threads go idle, and we only have 2 threads left going, the hardware will detect this. It will, and by idle, I mean the operating system is truly not dispatching anything on that thread and has done a nap on that thread. The hardware will detect it, and on its own, it will move the threads to the appropriate thread sets to balance it between the 2 sides, and then it will dynamically allocate the resources as if it was in SMT2 mode, even though the software thinks it's running in SMT8 mode. That way, if the operating system realizes that it has to activate those threads, it can activate them very quickly. The hardware will rebalance itself again and will move to the appropriate SMT level. We made a bunch of changes into the core. I told you we widened it. A lot of it was done in the vector scalar unit. In many cases, we doubled the capability of executing instructions. And then the other thing we added is we added a crypto unit and a user mode crypto unit, which I want to talk about real briefly. On Power 7, we had a on-chip encryption unit. And that was great for large block things like file systems and network. Very fast, very efficient, but you had to make the call, the hypervisor call to actually do that. In Power 8, we've optimized, in addition to having that for the large blocks, we've optimized a user mode facility, which is just a core instruction for user mode programs to use. And this has been incorporated in things like OpenSSL on our common operating systems. As you can see, we made some significant improvements in cycles per byte on the common encryption algorithms. And also, I've picked a couple of different workloads. CERT crypto AES is obviously that's almost all encryption, so you'd expect that to have a big improvement. SPECJBB 2013 was kind of surprising because that got a nice little 10% improvement just by having the hardware encryption. So how do we do on other workloads? Well, first thing, let's look at single thread performance. We've got a batch job that we have. It happens to be an IBM I job, which is essentially doing something like creating a zip file. It compresses a library of files. Excuse me. And this job is sensitive to runtime. You want to get it done as quickly as possible. So how quickly the job gets done is important. And you can see what we have here. The line graph is response time, and the bar graph is throughput. And you can see going from Power 7 Plus single thread to Power 8 single thread, the response time actually went down, and therefore the throughput went up. If we went to SMT4 on Power 7, we'd have a fairly substantial response time penalty, which could be a problem on this batch job. Power 8, go all the way to SMT8, still get decent response time and very good throughput. So how do we do in other workloads, kind of general purpose workloads? Well, if you remember last year, Jeff Stukley showed you some estimated performance that was based on our modeling results across a variety of workloads. And what I've done is I've put those in gray, and I want to remind you that's on the enterprise scale-up system, and that's a system that we haven't announced yet. We put a statement of direction out that we will announce it, so expect it to be coming. But these were based on estimates. The blue is what we've actually measured on the scale-out system. And you can see, this is basically my report card, by the way, is that we've done really well. The commercial and integer can be explained because differences in the product offering. If you want afterwards, I can explain some of that. The Java one is surprising. You'd expect that to track to commercial and integer, but we've put a lot of work, including some of the dynamic optimization I talked about, to make Java better. And I think it shows that we did a really good job there. And lastly, comparing how do we do to other processors, other systems in the industry, is looking at other 24-core scale-out systems. You can see in Java, in integer, and floating point, we're at least 2x, roughly 2x better than the other scale-out systems that are in the industry. So I hope you'll agree that, as I've shown, it's clear that Power 8 was designed for big data and analytic workloads. We've gone after strong processors with lots of cores. We have a rich memory subsystem, a lot of memory, very fast memory, and we have an impressive data bandwidth and I/O bandwidth to feed those cores. That's it. Other questions?
Okay, it's now, as they say in the British Parliament, question time.
My name is Tadao Nakamura. Cool Chips Conference Series. Okay, could you show me the breakdown of power consumption of the processors? For example, categories would be instruction supply or data supply, logic.
No, you wanted to know about the power consumption?
Yes.
That's not within the scope of my paper today. I'm sorry, I don't have.
Okay, I'm a Cool Chips people, so therefore I'm interested in such a thing. Okay, thank you.
Okay, thank you.
Thank you.
Okay. Yes, next.
I'm Sanjeev from Oracle. Just two questions. Your CAPI address space is mapped into the peripheral space or memory space?
I'm sorry, can you?
For your CAPI,
Yes?
address space is mapped into the memory address space, or is it mapped into the I/O space?
Oh, no. That's the beauty of CAPI. It's the memory address space.
Okay.
So what you do, and there was a question about how you handled addressing and coherency. The CAPI device uses the same page tables that the processor does. So you actually would say, I want a region of memory that's shared between the CAPI device and the processors, and the page tables and the cache coherencies handled it. So the programming model, instead of being an I/O model like it is traditionally, all the program on the processor, and it could be a user mode program, by the way, just needs to write into that address space. The CAPI device recognizes that its cache state has changed, wakes up, and starts working on it.
And the second part is that address space which you have on CAPI, is that you said it is 16-lane PCI Gen 3, which is kind of 128 gigabits per second. Is that the bandwidth you have?
Yeah. What we do is we tunnel over the electricals. I don't have the exact bandwidth to the CAPI device. We don't actually talk on PCI protocol itself. We just tunnel over through the electricals.
So the physical interface is same as PCI
Yes.
Gen 3?
Yes, but we actually tunnel our SMP protocol over that.
And just one last question that.
Maybe you should get in the back of the line again. Okay, yeah.
I'm Babu from FI Networks. Can you please talk a little bit about VMM assist?
No. Not in the time allotted. Is that we have some capability on the chip that allows us to basically data mover type assists. And it's not in the scope of the paper that I have today.
The next speaker is our general chair, so he certainly gets his shot.
This is a quick one. Chris Rosano at UC Berkeley. So at the beginning, I noticed you said that when you saw the die in half and put two of them together, you said the performance profile is the same as the big chip.
Yep.
So why on earth did you do the big chip?
Well, the main reason, remember I said, these are going into one socket and two socket systems. And we really want to use CAPI in these systems. And one of the big things we would lose if we just use the big chip is we'd have to take half of our I/O cable.
So the question is, why did you do the big chip?
Why?
The performance is the same. Using two small chips is a lot cheaper than using one big chip. Why did you ever do the big chip?
Because that one is optimized for scale up with larger S&P. And there you have a lot more sockets, so it's okay if you dedicate those lanes to CAPI.
Okay, so the performance profile isn't the same for the two small as the big in that application.
That's a semantical discussion.
Okay, you get your last third of a question if you want to do that.
So on CAPI, you can connect to the flash arrays. Is that right?
You can connect to
the flash arrays.
As an example, yes.
And you say that it's a coherent, right?
You
said it is a coherent address space.
Yeah. Well, yes.
And the flash latencies are nowhere comparable to the DRAM or any other the cache's latency. So can you expand on that? How do you handle that?
Well, that's next year's paper.
I think we've got an upcoming submission. Okay, well, thank you very much. I enjoyed the talk. I hope everyone did. Okay, our next speaker is Stephen Phillips. He's a senior director of the SPARC microprocessor architecture group at Oracle in Santa Clara. He's been with Oracle and Sun Microsystems for 11 years. He led the architectural development of several Sun's microprocessors, including the T2 Plus, aka Victoria Falls, subsequent generations of the T-Series microprocessors, the highly scalable and reliable M5, M6, and 7th generation Oracle SPARC processor, the focus of today's talk. Prior to Oracle and Sun, and this reminds me of these people who say, you know, I've been in the same desk for 30 years, but I've had 10 jobs at 8 companies. So prior to being at Oracle and Sun, he was co-founder of a startup company, and prior to that, he spent 16 years at Burroughs and Unisys, developing mid-range servers and mainframes. He has a master's and bachelor's in electrical engineering from Rutgers. And his title, which I guess I should give you, is Next Generation Oracle SPARC Processor. Steve, you want to come out?
Thank you, Alan. I'm here to reintroduce everyone to the M7 processor. We had a very good presentation earlier in the session with RAM and SMPTE. So I'll cover a few other things in the processor overview. Here's the legal statement. Again, it's a technology disclosure. I won't be discussing product plans or specific physical attributes of the processor. For those as a background, SPARC at Oracle, we've delivered 5 processors in 4 years. Currently, we're shipping our T5 processor in the center of your screen. We're shipping that in our 1 to 8 socket servers, and then the highly scalable SPARC M6 on the other end of the screen. We're shipping in our 8 to 32 processor, dynamically reconfigurable, hardware partitionable, hot maintenance, highly available servers. The Oracle SPARC strategy is what formulated the M7 and highly influenced its design. 3 of the attributes where we were looking for extreme performance. That is a step function in performance. We weren't looking for incremental. We really wanted to enable new services that previously were not economically attractive. Again, the second leg was to focus on computing efficiency with flexible virtualization, high consolidation ratios, and designed to have the applications run on highly available servers. And lastly, optimize for Oracle software. We work closely with our operating system hypervisor, database, middleware groups to optimize hardware and software, engineer them together, and it's resulted in a number of what we term as software and silicon features that are now available on the processor, and we'll talk about those. For those interested, you want to learn more about performance and price performance of our SPARC servers, I recommend you use that link there, and there's some very good presentations on that. Here's an M7 processor overview. You've seen this one before, so we all know. Here's the die photograph, 32 cores. We had very detailed and excellent discussions on the shared level 2 data and instruction caches and the new 64 megabyte shared and partitioned L3 cache. We're introducing DDR4 DRAM, continuing support for PCI Generation 3. I will talk about some of the software and silicon features specifically for accelerating dimensions of applications, as well as for scaling applications with our coherent memory clusters that we'll be releasing. And the SMP scalability of this processor now ranges from 1 to 32 CPUs. It was fabricated in 20 nanometer technology and 13-layer metal. Here's the core of the processor, designated S4. It was an enhancement to the S3 core that we actually discussed at Hot Chips, I believe, in 2011. It's still a dynamically threaded core with 1 to 8 threads. Dynamically threaded means that the resources of the core and the various arbitration points in the pipeline are continuously updated and optimized for the amount of threads running on the core. We increased the frequency at the same pipeline depths. It's a dual issue out of order execution core. We made some cryptographic performance enhancements, specifically around elliptic curve cryptography. We included a new power estimator. One of the things we did in virtualized environments was we improved the performance of live migration. That is the ability to take an application running on one server and while it's running, move it to another server. Or running on one physical domain, physical partition of a server, and move it to another one. We have core recovery, which allows us to extract the state of a core, take that state, insert it into another core, and restart the instruction. And a number of the software silicon features that we had to be integrated, support had to be integrated into the S4 core. Here's a core cluster. I won't talk much about this. It was covered in very good detail before, but we did arrange the cores into a cluster with multi-ported shared L2I and L2D caches. The key points here is we were able to have a 50% larger cache. Even though we increased frequency, we did not increase cycle count latency. We doubled the bandwidth per core. That's 1 terabyte per second per core cluster and over 8 terabytes per second per chip. That allows us to do some flexibility with core pair dynamic performance optimizations. So we can take an application running on an existing T5 or M6 system, take those threads, the application threads over, and put them on the core cluster. Now, since we're now sharing an L2 and a very powerful L2, high bandwidth L2, we can decide to divide those threads between the 2 cores in the cluster, since now the L2 is the coherence point for the core. That maximizes our per thread performance for response time processes and response time driven applications. Likewise, we can take those threads running on those cores on T5 or M6 and move them core for core onto the M7 core cluster, and that maximizes our core throughput. Here's a dissection photo of the, wrong pointer. There's a dissection of the speeds and feeds of our L3 cache and on-chip interconnect. I won't get into the details on it. It was very well covered. Again, it was a 25% reduction in local L3 cache latency, over 1.6 terabytes per second of L3 cache bandwidth, which was 2.5 times our T5 processor and 5 times our M6 processor. You've all now understand and seen in very good detail how the cache lines can be replicated, migrated, and even victimized between partitions, and details about the on-chip network. That core cache partitioning that you see here that abstraction now has visibility into the Solaris thread scheduler. User configuration or application programming interfaces. An application can actually tell Solaris how it wants threads to be allocated across the core cluster and L3 cache partitions. That abstraction is then raised another level up to the Oracle Virtualization Manager so that logical partitions can be allocated on a core cluster and L3 cache granularity. Another thing we did in the power management area was to focus on maximizing performance at a given power point. So we brought the power control unit on die. It takes estimates coming from all the cores, other inputs, other sensors, and generates a highly accurate power estimate on a per quadrant basis, which is outlined in each red box. It then individually adjusts voltage and frequency within each quadrant based on software-defined policies. That allows us to optimize performance at a power point where we're highly responsive to workload dynamics and workload non-uniformity between quadrants. In periods of idle time, we can actually power gate individual core quadrants. As far as memory and I/O, again, 4 DDR memory controllers. Each controller has 2 schedulers, very large memories up to 2 terabytes per second. We've measured on the test floor 160 gigabytes per second using DDR4 2133. That's 2 to 3 times our current generations. A RAS feature we added was dim retirement. In a running system, for specific reasons, we can decide to offline a DIMM and before offlining, migrate the data on the DDR4 channel across the other 15 DDR4 channels, and then offline that DIMM, and do that in a running system. We use memory links to buffer chips, where those link rates are tied to the DDR4 frequency. We talked about speculative memory reads in the other presentation, and that is a way of reducing memory latency, utilizing the prefetch buffers in the memory, and that's done on a per request basis based on history data for both instruction and data cache, instruction and data tracking. The PCI Gen 3 links, the 4 links support over 75 gigabytes of data bandwidth, and that's more than 2x our previous generations, T5 and M6. On the test floor, here's some processor performance over a pretty wide set of workloads that we've been running. Those are against a highly tuned M6 system baseline. Again, we're 3 times the memory bandwidth, and across a wide range of throughput applications, we're anywhere from 3 to 3.5 times the performance of our flagship M6 processor. For example, if we take Java, so that looks like it's around, say, 3.3 times M6. That also represents a 24% improvement in per thread performance with both processors running at max thread count. The per thread performance can increase again using the core pair dynamic performance optimizations I talked about early in the presentation. Okay, so now I want to start to talk about some of the application accelerators. This is where we've worked closely with the Oracle software teams and found ways to help take some of the software pains that they have and move them into silicon. And one of the first ones we did was application data integrity. This is in the hardware, in silicon, we provide real-time data integrity checking for both test and production environments. Very large, complex software systems developed using powerful programming languages, high-performance programming languages like C and C++. They periodically have to run diagnostic verification software looking for invalid and stray pointers and buffer overruns. That's done in a software development environment. It's very performance intrusive because now every load and store has to be instrumented. It's performance prohibited in a production environment. So what we did is we took that software and migrated it into silicon here. And we did it by associating a version metadata with every 64-byte aligned memory block. The metadata is stored in memory. It's maintained throughout the cache hierarchy and through all the interconnects. Even when I talk about the coherent memory clustered systems, that metadata is even transferred across the cluster. Over on the right side in the screen, as the core pipeline's executing, the load store units is constantly checking the expected version against the actual version that's provided by memory or by the caches. That enables applications, when there is a mismatch, to inspect the faulting reference, diagnose, and take appropriate recovery actions. And that happens real time in both test and production environments. Another thing we did for, in this case, the middleware, again, much software is written in Java. Java is a managed runtime, and managed runtimes periodically have to migrate fine-grained objects into new memory regions and reclaim the memory space of old memory regions. Typically, that requires halting or pausing the application threads. As these heap sizes grow, that application pause time gets longer and longer and less deterministic. So what we've done is we've integrated in silicon hardware support for fine-grained access control. What we do is we distinguish one of the metadata values specifically for migrating objects. That allows background threads, shown in black, that are, as they are relocating objects at very fine grain, just to mark those objects as migrating. Then, as the application threads are running, the only time they conflict, it then creates a user-level trap specifically on a migration fault, and there's a local conflict resolution that can occur very deterministically. That enables concurrent and continuous operation for our middleware memory migration of fine-grained objects. Another thing we've done in our middleware is many times when an object's accessed, the runtime needs to insert barriers, whether they're for every time the object's read or written based on the runtime implementation. As part of those barriers, it typically needs to look up into data structure specific attributes about the object, and that's right in the critical path of the object access. So what we've allowed the runtime to do is to embed its own user-specified metadata into the 64-bit virtual address pointer. It's ignored by the effective address hardware. It operates, it coexists with the memory metadata for application data integrity and migration. And it allows the runtime to, in effect, cache object state and eliminate the dereference and the memory load from the critical path. Another thing we've done in the area of the database in-memory query accelerator. This is a set of in-silicon query engines focused on, they are optimized for the Oracle 12c database in memory. They're task-level accelerators that operate on the in-memory columnar vectors. So on the left side here of the screen, the Oracle database, the in-memory database, operates in both row and columnar formats. The columnar formats can be compressed or uncompressed. The query engine operates on both and performs a number of different functions. It can do format conversions. It can do specific predicate evaluations like value and range comparisons. It can do set membership lookups. It can also fuse the decompression stage with the predicate evaluation so that only the filtered results are sent out into memory or into an L3 partition. So that fused decompression and query function further reduces task overhead by reducing the number of calls. It reduces core processing cycles, as well as providing better memory bandwidth per query. Here's a closer view of the query accelerator engine. There's 8 of them. Each engine has 4 pipelines. They share a common local SRAM, and the macro stages are they decompress, unpack, and do alignment, do the predicate evaluation, and then format the results, do the encoding that's necessary, and send out the results. Each of the accelerator engines are attached to the on-chip network, the very high bandwidth, low latency network, so that the cores and threads operate synchronously or asynchronously to these offload engines. We've introduced new user-level synchronization instructions for the cores to synchronize with the accelerators through shared memory. These accelerators provide very high performance at low power. Here's an example of how the cores interacts with the hardware accelerators. So the core thread will generally initiate a query plan task offload to the engine as part of an overall query plan. Initiate that call, it will start the hardware accelerator. The hardware accelerator will start doing whatever it needs to do, decompression, predicate evaluation. It will start writing its results into memory or into a target L3 partition. Concurrent with that, the core can continue operation, and at some point in time, it executes a sequence of load monitor, and M-wait instructions. The M-wait instruction stalls the core waiting on an update to a specific memory location. And that's going to be the location where the hardware accelerator posts its completion status. So when the hardware accelerator is done, it posts to the monitor memory location, and that unblocks the core without any OS intervention. That allows the hardware accelerator to operate on relatively short vector lengths, and they're actually just percentages of the overall compression units in the Oracle in-memory database. Here's a query offload performance example. Here we took a SPARC T5, which has currently our highest memory bandwidth, and M7, both running the Oracle 12c database in memory. We did a single stream decompression performance where we just took a set of unaligned bit-packed columnar formats and performed a set of predicate evaluations on them. We just did it on one of the 32 query pipelines and one T5 thread running exclusively on a core. And you can see we have better than a 10-to-1 performance improvement. And that did not include the hardware accelerator's ability to fuse the decompression operation with further filtering operations, which would further accelerate the where clause in the SQL query. All of those software and silicon features I talked about were really targeted at Oracle, the operating system, the database, the middleware. But they will also be available to third-party software. There will be a SPARC accelerated program where all of those items I talked to will be available either through relationships on Solaris with the compiler and the tools chain, and even through various software libraries. I'll finish up with some talk about scalability in our memory-based clusters or coherent memory clusters. So our M7 scalability, we have 1 to 8 socket scalability through fully connected systems. That's up to 256 cores, 2K threads, 16 terabytes of memory. You can see over a terabyte per second by section bandwidth. It's a topology that's identical to the T5 systems. We build our smaller SMP systems with utilizing link trunking for 2 and 4 processor systems. We use directory coherence just like we do on the T5 systems, and we up the link rates between 16 and 18 gigabits per second. So it supports the dynamic congestion avoidance just like T5, where if a path is congested, we can route around, and all of the same link level RAS features we've had on our T5 system. Our large systems, our M6 systems, our SMP scalability is now to 32 processors. So that in the M7 case, that's 1K cores, 8K threads, and up to 64 terabytes of memory. The center of the topology is a set of 64-port switch ASICs. They're divided into 2 switch groups, which are color-coded here. The links are color-coded, blue and magenta. There's a 5.2 terabyte per second bisection payload bandwidth, which is 4 times our M6 systems. So the physical domains or building blocks are 4 processors each, shown in the dotted block box. So you can collect them together, divide them apart to build single image 32 processor systems or hardware partition systems of any combination using those building blocks. Those building blocks are fully connected locally and fully connected to the switch ASICs. There's 2 links from every processor to every switch ASIC. And the coherence directory in the case of our large-scale systems is distributed across the switch ASICs just like it's done on M6 today. However, we now have no indirection to get to the directory, so we've got a latency improvement. And the SMP interconnect RAS is all of the low-level SMP, or 1 to 8 socket features, plus link-level multipathing, and the switches are operational with 5 of the 6 switches operating in each group. I'll finish with coherent memory clusters. It's a new, highly reliable, and secure shared memory clustering technology. Integrated within each M7 processor is user-level message in RDMA messaging facility. That's already there. On top of that, we built access to remote node memory, basically shared memory semantics using load, store, and atomics with a relaxed ordered memory model. So memory segments on another server. So on the picture here, these are independent servers building out the cluster. So a server participating in a coherent memory cluster can access a remote segment. And it's done that by a given server exporting a home segment, shown here in yellow, and the other servers importing that segment as a remote segment. When that's done, the remote segments act as memory caches, so that any load hit to those remote segments are just as fast as local memory on that same server or the local cache latencies on the same server. Stores that are committed into the cluster follow a relaxed memory order, a relaxed memory model. So the committed stores update the home node always. In this case, the update from A, the value A to A prime, and they invalidate the caches and the memories, the memory cache in the other nodes. Non-cacheable segments, all the way up at the top, always access remote memory and it's never cached. That's the memory model. We maintain security by establishing a 64-bit access key, and that by each home segment, it's then exported out to a remote segment, and it's checked on every request. It can be revoked at any time to provide security, and like I said before, the memory version, the metadata that we check even on the same server is also checked on the cluster. So the technology is highly reliable and secure. Here's the coherent memory cluster topology. It scales up to 64 processor clusters. These are actually independent servers. I'm showing 4 processor servers, but they can actually be any combination of 2, 4, and 8 processor server nodes. They leverage the SMP hardware interconnect, and the changes we made to the cluster protocol for reliability was we make sure that the committed stores can remain consistent at the home nodes in the face of failure on the requester, in the face of requester failure in order to recover the cluster. And we only use two-party dialogues to simplify our failure isolation. The switch itself is fully redundant, using the same 64-port switching ASICs. We don't use the directories. It gives 6 switching paths for every processor pair. They're divided into 2 groups, and we only need 1 switching path per group. So it can actually take 2 failures or a number of failures per group. We use automatic link and switch failover without involving the application software. So the clusters, the memory model is one of an SMP style model. They're very secure, using 64-bit keys and reliable through the cluster protocol. So in summary, M7 and extreme performance, we had a 3.5x increase in overall processor throughput. We further increased core and thread performance, both natively and through the core pair dynamic performance optimizations. We increased bandwidth across the board, caches, memory, interconnects, and I/O. Very large memory, 2 terabytes per processor. In the areas of computing efficiency, we increased our virtualization density. We offer now lower application migration, live migration support. There's very flexible, both logical and physical partitioning in the technology, and we improved our power management to finer granularity. The M7 was optimized for Oracle software. We improved both security and reliability via real-time application data integrity checking. We offer the ability for concurrent object migration and pointer coloring, and the database in-memory columnar decompression, query offload, and coherent memory clusters. Thank you.
Okay. Thank you very much. As now, again, question time. Okay, now we have our General Chair in waiting this time, Fred.
Did I understand correctly? You can put 64 servers into a memory cluster and 16 terabytes per memory cluster, so 3/4 of a petabyte of main memory in a cluster?
We can put 64 processors in a cluster at 2 terabytes per processor.
That's disappointing.
Yeah.
All right.
I thought so, Fred. I thought you were going to say that.
Okay, next.
Hi, Mo Hagikat from Intel.
Oh, sorry, I didn't.
No
the
problem.
microphone was empty when I looked over there. Go ahead.
So, how much performance improvement do you see in garbage collection of Java benchmark like SPARC JBB or
I can't share that.
You can. Okay, thanks.
Could you speak up a little bit? He's having trouble hearing you.
Oh, I asked how much performance improvement do you see from in garbage collection of SPARC JBB or any other Java benchmark as a result of hardware support for fine-grained object migration?
Right, yeah. I heard the question, and I can't talk about a specific benchmark's product related, and I can't talk about that. But it will come out.
All right, thanks.
Okay, yes.
Jen Lee, Huawei Technologies. A question on the in-memory Curie accelerator. Is it a coprocessor? And what's the sort of a peak input-output data stream bandwidth for that?
It's a coprocessor in the sense that it runs concurrently to the thread, right? But it is truly dedicated hardware optimized for the Oracle database in memory.
And can you also share, if you can, if you want to, on the data streams bandwidth?
And what I can tell you is that the 32 query engines have no trouble saturating all the memory bandwidth we can feed it.
Bill Rash, Intel. I have a question about the metadata you use to attach to cache lines, and you mentioned the slide says it operates at high performance. So I'm wondering if you could say some more about how you try to avoid an extra memory access to fetch the metadata when you fetch a cache line to save performance.
Yeah, hi Bill. We don't fetch another cache line.
But the data is still separate, so it had to be somewhere.
No, it's in line on the DIM.
Thank you.
Ah, yes. Nathan.
I don't know what to do with that, Alan. Question on the physical link technology between your server nodes and your switch. Can you comment on how that works and what the distances are between the nodes and the switch?
Let's see, can I comment? Well, the link speeds are anywhere from 16 gigabits per second to 18 gigabits per second. It's hard to comment on the product because that's a physical nature of the product. But you know, a 32 processor server is bigger than a 1RU box. So I mean, physically it's bigger. But I can't really get into what the actual...
Can't get into how spread out that could be. I mean, do these things have to be in close proximity to one another?
I just can't. I mean, the products are running in the lab. I just can't comment on them.
Okay, thanks.
Just think big iron. And now we have a David Patterson.
Yeah. David Patterson, UC Berkeley. Since you were at Sun before Oracle,
yes.
If you set aside the application accelerators, can you comment on what the big changes were for designing SPARC servers for Sun versus designing SPARC servers at Oracle?
The major focus, really, I agree with you, was to focus on optimizing the Oracle middleware and the Oracle database.
But like, was it RAS features became more important now?
Well, anytime you scale up a processor, right, and consolidation ratios get higher, you have to increase availability, right? And you can see a number of RAS features that were put in for that. Exactly, right.
All right, thanks.
Yes, go ahead.
Hi, Yahya from Intel. Thanks for presenting. Slide 15. Can you support both generic metadata and version metadata in slide 15?
So on that slide, yeah. So what happens is in the virtual address pointer, we're actually using unused bits in the VA pointer. And then the metadata for application data integrity and for memory migration is separate. So in effect, what we're doing is we're condensing the VA pointer down from 64 bits to something less, whether it's 8, 16, 24, or 32 bits that the application asks for. So they're separate.
Okay, well, thank you very much for an excellent talk.
Okay.
Okay, before I introduce our next speaker, let me point out after the speaker, there'll be a few minutes of closing remarks. Program claims 20 minutes. I'll be very shocked if it's that long, so you don't need to run out before they start. Please do hand in your evaluation form. And so our last speaker is Irma Esmer. She's speaking from Intel. She's been there since she joined Intel Folsom in 1992 as a graduate student engineer. She later moved to Santa Clara. Over time, she worked on overdrive processors, processor microcode, performance modeling and analysis for Itanium processors, and then x86 product performance. She's now a principal engineer and leads the Santa Clara server performance team. She's responsible for power and performance of a number of next-generation Intel Xeon processors. She has a BS degree in Control and Computer Engineering from the Technical University of Istanbul and a master's in Computer Engineering from the University of Wisconsin-Madison. I think that first winter in Madison must have been a shock. And in 2009, she received an Intel Achievement Award for her contributions to the Nehalem EX project. Irma?
Thank you, Al. Hi, everybody. Thank you for staying here, the last talk before the end of it. Happy to see it's still full. So today, I'll be talking about the IvyBridge server processor. And before I continue, I just want to make sure that we acknowledge the entire IvyBridge server team. It was a big project from architecture, design to validation, and we have now successful products in the market. So here is our obligatory die photo, and also you might have heard it as IvyTown. It's the same thing, IvyBridge server, and it was launched into two different server segments, into the E5 product line for where prior generation was the SandyBridge E5 line, and in that segment, we got up to 50% performance increase with this generation. And in the E7 segment, where the prior generation was the Esmer E7 4-socket product line, in there we got, I say up to 100, but actually you have publications where you can see up to 180% upside. So in this talk, I'd like to share with you the challenges, our primary goals, and also share a few details that you might not have seen before. So to start with, our primary goals when we started the IvyBridge project was we wanted to design one converged architecture. And with that one architecture, wanted to cover the entire server spectrum, our entire portfolio. So after achieving that, of course, our next key goal was to get to scale. Oh, I'm sorry.
The spotlight on her just went out.
Is this good?
If you move over.
I thought that box was okay, but sorry. Okay. So thank you. Our next goal was, after getting that convergence in line, we wanted to make sure to get the scalable and energy-efficient performance. And of course, our final goal was Intel process technology, 22 nanometer. We wanted to take advantage of the features that the technology could offer us. So let me first talk about covering server space. What does that really mean? For those of you who are not familiar with the Intel product line, we have the E5 and E7 product lines. And the E5 is where we have our efficient computing, entry-level servers, workstations, high-end desktop products. Those all go in that from that E5 line. And then we have the E7 line, where it's the expendable and mission-critical servers. And both lines are scalable. They do go into up to 4-socket glueless systems. The E7 line, however, can do all the way to 8-socket glueless system, as well as all of them, well, E5 and E7, they both go also into not controller-based scalable systems. So historically, when we supported these two segments, we ended up building two different products and two different platforms. And to do so, we used the same core, but we ended up building two different encores and effectively two different designs with two different teams and the entire design and validation backend. And of course, in doing that, we ended up introducing the two product lines not immediately back to back. E5 used to be leading E7 by roughly a year. So our challenge was in IvyBridge server to cover both segments, and they were fundamentally different segments too, not that similar. So both be able to support the high end, as well as efficiently scale it down to the lower SKUs that we needed to support. So let me first talk to you about the converged architecture. It's no surprise to be able to do the convergence. We needed to support the superset architecture that needed to supply, the highest end of our SKUs. So here is a microarchitectural view of our base design, our base die, basically, where you see there are 15 cores and cache slices. And if you look at them, the cores are stacked in groups of 5, and across from them, there are the last level cache slices, 2.5 megabytes each. And they are repeated. We have 3 columns of cores and caches in this product, hence the 15. And we then have 2 home agents and memory controllers on the bottom of the die, and we need to support both native DDR as well as buffered memory. Again, because we are going both into E5 as well as E7. And on the top, you see the QPI agents. The one on the left has 2 links coming out of it, and the one on the right has 1. So we have total 3 links, which allows us to do 4-socket glueless for the E7 line, as well as go all the way to 8-socket. Of course, the PCIe lanes, I/O, integrated I/O, comes to this product as well, just like in the prior generation, and we needed to support the needed capacity and the number of lanes that the maximum of our segments needed. In this case, it was 2 by 16 plus 1 by 8, so total 40 PCIe Gen 3s. Advanced Rust features also are an important part of our E7 line, and they are not, of course, in a single cluster. They are kind of scattered everywhere in the architecture, and that was also supported. So now that we covered the overall feature set and the architecture, the base design, how do we end up going from this large base design to really scaling it down efficiently all the way to our workstations and high-end desktop? That was one of our challenges, and we did that via chops. I'll talk about that in the next slide. We also ended up making everything quite configurable because, again, we listened to our customers, and with their feedback, there were customers who needed, a certain number of cores, but not more. Right? Because some of the licensing fees are quite high, and they needed high-performing cores, large caches, but not necessarily all cores in every SKU. So we ended up basically enabling, disabling number of cores and cache slices and so forth, and those happened with fusing. Here is our die photo again, talking about how did we end up going from this, again, large base design to our smaller dies, and from the 15-core to a 10-core and a 6-core design or die that we have. So in order to do that, we ended up, you can see actually it's quite modular too. Before the light shaded areas are our cores, and the darker ones in the middle area are the caches, and they are laid out in a modular way. And so we were able to actually remove the right column with the 2 system agents on the top and bottom. And that's how we ended up with our 10-core die. Now, 10-core was all good, but we needed to go even lower. To go to a 6-core, we then needed to go and remove the rows of caches and cores as well. So that's how we ended up with our 3 dies, which end up serving our 3 different sockets, 2 different platforms, and at the end we have 75 plus SKUs that we support with this product. So now that we went through the convergence and how we did that, then the next thing was path to performance. So here are the 3 components: core performance, core improvements, socket performance features, and then our 22 nanometer process node. So the core, we got about 5% increase, and I'll be touching upon all of this, particularly on the second and third one in the next few slides. The socket performance features, you saw the large number of core and cache size increase. That was all good, but we needed also to make sure that we can get high cache bandwidth, not just the cache size. Then also, we needed to improve our memory bandwidth. Everybody else ahead of me talked about the importance of memory bandwidth, no need to repeat it. And our customers, especially the HPC customers, were quite adamant about getting more and more bandwidth. So we listened to them and we emphasized it quite a bit. And the next thing was, of course, efficient scaling. We needed to scale it across on die, and as well as across sockets. And then came the 22 nanometer, where we got our system level performance per watt increase as well. And we were able to maintain high frequencies with the core count increase. So a bit about the core. It's the IvyBridge core. It's a core that was disclosed before and was used in our mobile and client products. So the feature set is the same. It comes to the server, and roughly it gives 5% general compute IPC increase. Of course, this is comparing to the prior generation SandyBridge core. If I were to compare E7 line, remember, had the Esmer core before, so that prior generation was the Esmer core. So over that core, it has significantly more upside. But the beefy core is good. That's what we need, and we used what was available for us at the time. And all the core features, ISA additions, and microarchitectural features came with it. Of course, I'm not going to go through the details of them, but you can find them, if you like, on the Intel websites. The key thing I want to talk to you about is our scalable on-die interconnect. So, okay, we put all the cores and caches together. How do we really connect them? We did not want to build a massive, large interconnect that could take a large area, die area. I've been showing these 3 rings all along, but how do we really make those 3 rings? It's really 3 virtual rings. You are all familiar with the prior generation polarity-based ring architecture. It's simply an extension of that. And to extend it, what we did was we put muxes on the top and bottom of the columns. And with those muxes, you can see we have on one setting of the mux, we go one direction, and you can see that we are enabling 2, for instance, in the picture here, I can see better with my eyesight getting worse. The inner rings going counterclockwise on the left picture, while the outer ring is going clockwise. And then in the other mux setting, we enable the exact opposite, and we do the counterclockwise outer ring and clockwise inner rings. So that's effectively our interconnect, and it allows us to get still great scaling. We get roughly 9 bytes per core per cycle for LLC accesses, and in a 15-core die in our EX product, we get, I think we have been measuring 450 gigabytes per second on socket LLC hit bandwidth. And basically, this is how we achieve the low latency and scalability. Next thing was, as mentioned earlier, memory bandwidth. We heard customers, they wanted it. First easy thing was to go increase memory speed. We went to 1867. This is again in the E5 platform compared to the 1600 before. It was an uptick, roughly 17% memory speed upside. And that was not exactly enough. We were increasing the number of cores quite a bit. We wanted to feed them as well. So we kept looking at other opportunities. You see that we have doubled the home agents and memory controllers. That in itself increases the number of buffering, of course. But beyond that, we looked at the home agent a little more carefully. Home agent is our basically the engine that controls and manages the coherence for transactions that are coming to DRAM of that home node. So in there, we had in prior generation 128 entry trackers with data buffers. We kept that as is, but we added a second level, or you may call it first level. So we have a first level 512 entry tracker, which is then backed up by our 128 entry tracker with the data buffers as well. And this enabled really bringing all those transactions, particularly for remote sockets or multi-socket traffic, to bring them closer to the memory controller and get the efficiency higher. Then looked at the memory controller queues and structures, increased them as well. 48 and 32 entries for read and write buffers in the memory controller per channel. And then one more thing, I mean, after doing all that, we did not really want to end up not having good efficiency. Our goal was to hit at least 85% efficiency for read-write type traffic and 95+% efficiency for just 100% read traffic. And to achieve that, we looked at our traffic mixes, and we basically looked at some of the optimization opportunities. And you might have read opportunistic read scheduling within write major mode, or tuning our write watermarkings and so forth. Those are the things we did. In addition to that, I think we have also a channel interleaving option that we enabled with A7 so that we can get better page hit rates as well. So that was how we increased our memory bandwidth. Next thing was buffered memory solution. As I mentioned earlier, needed to go and cover the E7 segment as well, where memory capacity is really important, as well as, of course, advanced RAS capabilities. So for that, we again go to a memory extension buffer. We have 4 SMI2, we call them Scalable Memory Interface Generation 2. In prior generation, Esmer E7, it was SMI1. And so with that, we can have up to 8 DDR channels in the back per socket. And on each channel, we can have up to 3 DIMMs per channel as well. So total DIMM capacity is quite significant, maybe not comparable to the prior Power 8 and the other talks, but in this segment, we have 24 DIMMs per socket capability. And we can go quite a bit of, today we have products using 64 gigabyte LR DIMMs, and you can just multiply and see what that capacity is. Quite significant. And we have 2 operation modes here. One is our lockstep operation mode, which is the high reliability mode. And we also enabled in this generation an independent channel mode to enable, again, higher bandwidth for our higher number of cores. And in that one, we ended up going with, for the lockstep mode to improve performance, we actually go there up to 1600 DDR speed, while for our independent channel mode, we go to 1333. Though we go only to 1333 DDR3, we enable our SMI2. We run that at twice the speed of the DDR3, and that's how we enable the higher performance as well. Resulting memory performance. After talking about all these features, putting it all together, what you see here is a little bit of an eye chart, but basically it's a bandwidth latency curve for 3 read, 1 write traffic mix from all cores simultaneously. And in this case, the first graph, the blue line you see, is our prior generation IvyBridge E5 2-socket product. Bandwidth hits a wall roughly in the 80 gigabyte range. And then when we put the red line, that's our IvyBridge E5 version 2 with the same memory speed. No memory speed increase with 1600, and you are getting a good upside of bandwidth at the same memory speed. And then when we go to the 1867, that's when we get another good boost. And altogether, we were able to increase it 23% for this experiment. And we have other experiments where we can go even higher. And here's another eye chart for you. You can read it later. It's in the proceedings. This is the E7 line. And you see the bandwidth increase is quite significant. Another thing I like to point out is those orange outlined rectangles on the left. And that's what I'm pointing out with that is the latency, how we are keeping it quite low. And though we are increasing the core count quite significantly over the prior generations, but we are keeping the latencies in check. Next, coherence optimizations. Well, after handling performance and scaling within socket, of course, multi-socket was quite important for us too. And in this product, we enabled in-memory directory, Snoop directory, for all system settings, not just for 4-socket and above. And we deprecated effectively the early Snoop mode. And this enabled us to improve our latencies. Basically, if the memory was clean, we did not need to pay the penalty and go Snoop and come back. That could be latency impact as well as power impact, because we didn't need to have those snoops going on our links. Second, we went from a 1-bit in-memory directory to 2-bit in-memory directory. This way, we were able to also track shared memory state. If a cache line was cached in multiple sockets, we really did not need to be snooping, right? We could get it from memory, and what was in memory was the right version. Nobody had gotten it. For ownership and writing purposes, it was perfectly fine to send it to the requester. So again, it was latency optimization, and it reduced Snoop traffic. Quickly, we also added a new Snoop mode. Again, the purpose of it was to reduce directory overhead. Since we were enabling directory even in 2-socket, we did not want to pay the penalty for our cache-to-cache transfers. And for that one, we speculatively enable snooping while sending the request also to memory. Well, we are going to say, if you do that, you are losing the benefit of not snooping and energy efficiency. Exactly because of that, we ended up implementing a dynamic heuristic in our home agent. So home agent actually, this feature is quite dynamic and quite configurable. First, it could be configured for different transactions differently, different thresholds, different enablement and disablement opportunities, as well as home agent will not generate a snoop, even if it's set enabled, if the interconnect bandwidth is not available. Secondly, also, home agent tracks the usefulness of the snoops. If it snooped, but it didn't really need to snoop because directory came back clean, we really didn't need to generate those snoops. So we end up tracking it and dynamically throttling it down. And if later on the program behavior changes and we actually need those snoops again, we end up increasing it, going back up to the levels we started from. Another quick coherence-related one is the I/O directory cache. Again, the purpose of this cache is reducing directory. And why did we do it for I/O particularly was because I/O really is not that localized. It doesn't only use local memory, but also goes quite often to system memory and all sockets memory. Hence, we wanted to remove the directory read and update overhead for remote I/O transactions, particularly I/O writes. And while we are on the I/O topic, of course, I/O performance was important. And one of the important features that our customers came back to us asking was virtualized small packet processing in our prior generation needed to be improved. To do so, we enabled the large page and super page sizes for I/O virtualization. And with that, we were able to achieve significant performance upside, as this graph could show. Particularly on small packet sizes, you can see the dramatic increase over IvyBridge E5 2-socket. Additional arbitration improvements and PCIe atomics were enabled as well. Last but not least, I'm sorry that doesn't look that good on that picture, but I want to hit a few bullets here. The 22-nanometer process is quite key for us. It certainly helped power efficiency. So here it is an eye chart, but a few things that I want to show you. The dark blue line that we have over here is our prior generation SandyBridge E5 two-socket system. Throughput on the x-axis and power on the y-axis. And what you see here is a few IvyBridge server E5 version 2s. So one of them is this light blue line. It's a 70-watt IvyBridge E5 version 2 versus the 95-watt SandyBridge E5. And you can see it is achieving same level of performance here, roughly 30% at roughly 30% less power. Quite significant improvement. And then you look at the dashed line, which is 95-watt IvyBridge server, similar SKU, comparable SKU. It's achieving 25% more performance at lower power, roughly 9% less power. And then the yellow line shows you our 130-watt high-performance E5 part that, of course, is focusing mostly on achieving great performance, and that's what it's showing you. And all of them, this is again shifted a bit, apologize for that, but all of them are improving the idle power compared to our SandyBridge E5 line. That the top one you see is the SandyBridge E5. So all in all, in summary is we tried to put a well-balanced system together, and we think we achieved it. You are seeing our products today in the market from practically high-end desktops, workstations, to cloud servers, as well as to our high-end servers. And we ended up refreshing E5 platform with this product, and we launched a new platform, again, on the E7. And altogether, we were able to cover and service quite a few SKUs. And our focus was, again, on balanced performance everywhere. We think we achieved that with all the improvements we put in. And our, again, another key goal was improve performance, but improve it when you need it. And hence, all the features we put in were kind of focused on reducing power if we can. If dynamically we could turn things off and throttle things down so that we don't end up using it, that was our purpose. And that's the end of my talk. Thank you.
Thank you very much. You can tell she's not a member of the Screen Actors Guild because a professional would have immediately figured out exactly where the spotlight was brightest. Okay, Nathan.
Yes, thanks for a great presentation. Question on the memory controller technology. You've combined both the ability to talk directly to DDR DIMMs and the SMI2 in the memory controller. Does that mean that an OEM can design a motherboard, say, for an E7 that uses the DDR memory bus, or that a user of E5s could take advantage of SMI, or do you fuse those options differently for the different SKUs?
Technically, basically, it's the, let's put it this way. We have 3 different packets, right? E7 packet will come out with different pins. So a customer who has designed a platform for the E5 socket won't be able to take our E7 part and plug it in. So they do need their different platforms still, but it is internally, it is the same die we built that served both segments.
So it's a convenience for Intel, but it really doesn't give the OEM customer any additional flexibility.
In a way, maybe you can think that, but on the other hand, the E7 customers got the parts much earlier than they would have otherwise. And they benefited from the technology's power efficiency features that we put in for our E5 line, which was more power constrained than our E7 line. So I think there is a good synergy.
And was there any socket compatibility between the SandyBridge and IvyBridge?
Yes, indeed there was, and that's why it was a refresh in the SandyBridge platform, that we tried to maintain the same socket. There was no change.
But probably not for Westmere.
Not for Westmere. That was a quite old platform. Yes, that was a new platform.
Okay, our next distinguished questioner is Don Draper, who is chairman of the Technical Committee on Microprocessors and Microsystems, who actually sponsors the conference.
All right.
So I guess Don gets to get his question in too.
Thank you, yes. Don Draper from Oracle. So my question is, your on-chip interconnect, what is the bisect bandwidth?
So there are multiple, it's shown as a simple ring, right? But it has, of course, a data ring. There's different types of rings. On the data ring, we can do 32 bytes per cycle, per core. So you can calculate that.
32 bytes per core
per cycle, yes.
On the data ring.
That's the peak, yeah.
And the other rings?
They all run at the same speed as the core speed. I don't know that I can give you details on those rings too much.
And those core speeds are what?
They are all listed actually in the backup of the presentation because Alan made me. Okay. But you can find the speeds all published in the data sheets are available on the website. For instance, I can tell you, it's from my memory, it's a little becoming distant memory, sorry, but 2.7 gigahertz is, for instance, our 12-core E5 version 2 top skew. TDP frequency. It can turbo up to 3 gigahertz, I think, as well. Yeah.
And one more. What is the coherency link data rate?
That is, it's we have, I'm trying to remember, I'm sorry, 8 gig of transfer per second is our QPI speed. And it is, I'll get back to you. I think it's listed again. I don't want to say anything wrong, but it's, that's the speed.
Thank you very much.
Well, thank you very much. That was a delightful talk. What Irma was referring to is when the speakers said, "Oh, I've got too much material," I just said, "Well, skip it or put it in the backup slides so that somebody reading can get all the information." What we now have is short closing remarks, and hopefully our closing remark speakers are coming out shortly. But we have Kirsty Asanovich, who's from Berkeley, who's our general chair this year, and Guri Sohi from Wisconsin, who's our program co-chair from this year. Sam Nafzinger has already, why don't you guys stand in the spotlight while you get introduced. Sam Nafzinger, who's the other program co-chair, had to leave. As you can see, these are the big men on campus. This year we went for altitude. Next year, we may be a little shorter in staffing.
Well, thank you. Thank you to all the presenters and the people who submitted presentations. I'm sure you'll all agree we had a wonderful set of presentations, a very impressive technology, very different from the i486, which is was my first hard chips presentation that I attended. And I'd also like to thank all the program committee and who really worked hard to solicit presentations, and the session chair who managed to get the presentation done on time. And the presenters, I believe for the first time we got all the presentations, at least the initial versions, in time for the hard copy proceedings to be prepared. So thank you to everybody who helped make this program a great success.
Okay, thanks. I'd like to thank Guri and Sam for leading the program committee. Did a great job. Very strong technical program, tutorials and keynotes. I'd also like to thank, one thing I should mention. So we have a wonderful program. We've captured it all on video. So in a few weeks' time, all these videos will be available online, password protected on the website, the program website. Please remember, this is password protected for attendees only. In December, we will be making it available to the public, and the whole set of previous year's archives are already up there and available online if you'd like to look at previous years also. There will be an option for people to purchase additional access before the December unveiling, public unveiling, if you'd like. So I'd like to thank our sponsors in particular, especially our platinum sponsors, Oracle and Intel. Thanks to the sponsors, we can keep this being one of the best value conferences, we think, in this technical area. And a big thanks to our sponsors. So, I'd like to thank the Flint Center to make a very smooth running operation here. We like this place. It seems to work well for us. I'd also like to thank especially all the volunteers. And without the volunteers, this conference couldn't be put on. I'd like to call out for special attention Lance Hammond, who's in the back. He's been installing everything, running the video, and not only that, this year he managed to put together a Wi-Fi system on his own, running around putting a few airports. I think it's been working marvelously well. Also like to thank John Sell, who made sure we got fed and got our ice cream. I'd also like to, special thanks to Scott Wakefield, who stepped in at the last minute when Charlie had a last-minute family emergency for registration. And it seems we've done a great job getting you all your badges on time. Plus, there's an endless cast of lots of the student volunteers and many other members of the volunteer committee. Just done a fantastic job. Made my life as general chair extremely easy. I didn't have to really do anything with all these volunteers. So thanks to the volunteers. Finally, I'd like to thank you, the attendees. They're the reason we hold these conferences. This year has been wonderful in terms of attendance. We hope you'll all come back next year, and we hope you'll help us improve the conference. So please return the survey forms in the boxes at the front. We rely on your feedback. So tell us, for example, if you like these long days with lots of presentations, or you want fewer presentations and shorter days, longer breaks, better Wi-Fi, better food, different food. We're really just trying to make this the best experience possible for you guys, so please tell us what you think. And so with that, I would like to close the conference and wish you well and hope to see you next year. So please drive safely on the way home. We've kept you late enough, you'll probably miss rush hour, so, okay.